What's up, everybody? Welcome to the Comet ML office hours. It is the final session for this is 8 weeks. We've been talking about this for 8 weeks about standardizing the experiment. Today, we are going to be talking about the last mile of machine learning, and that is serving and production monitoring. So tune in if these are things that you are interested in hearing about, because we're going to do a good deep dive into all this stuff. So let us go ahead and get some introductions done. So the first panelist I want to introduce is the head of research here at Comet. He's earned a PhD in cognitive science with thesis that use an early neural network trained to make analogies in symbolic relations and images. Prior to joining Comet, he was a professor of computer science at Bryn Mawr College, where he actually founded the computer science department. During his time there, his research focus was on using neural networks to control a robot that went through developmental stages as it seeked out interesting aspects of the environment, which has now become the new field of developmental robotics. He's also developed one of, if not the first, neural network simulators in Python, which used backpropagation with configurable layers. He's also one of the distinguished contributors to the Jupyter project and has worked on a project called Python Robotics. Please help me in welcoming our first panelist, head of research here, Dr. Douglas Blank. Doug, thank you so much for being here, man. Appreciate having you.
Thank you. Thank you very much.
So our next panelist is experienced in creating software tools for research in a research and development environment with a focus on novel, high-impact technologies. He's earned a bachelor's in mechanical engineering from the Georgia Institute of Technology and a master's in mechanical engineering from Columbia University in New York City. Prior to joining Comet as a data scientist, he worked as a research intern and research engineer at IBM. Please help me in welcoming our next panelist, my fellow colleague here at Comet, Dhruv Nair. Dhruv, thank you so much for taking time out of your schedule to be here. And our next panelist has a wide variety of interest in machine learning, ranging from computational paleobiology to AI for collaborative jazz improvisation and everything in between. He's earned a bachelor's degree in mathematical statistics and probability from the University of Arizona and a master's in computational statistics from Arizona State University. In his free time, he applies his math and programming skills towards creating code-based visual art and design projects. Please help me welcoming our next panelist and fellow colleague at Comet, Michael Cullan. Michael, thank you so much for being here today.
Thanks, Harpreet. Happy to be here.
All right. So I know you guys have already been familiar with Dr. Doug, Dhruv, and Michael, but I'm excited to introduce a new face to you here today as part of our panel discussion. He's got over 7 years of experience as a data scientist working on problems ranging from statistical analysis to fraud detection to Bayesian optimization, trip classification, and everything in between. He was also the founder of a company called Stackion, which monitors machine learning models that run in production for breaking changes and concept drift. Stackion was acquired by Comet in 2021. And since then, he's been here at Comet helping data scientists build better models faster. Please help me welcome our final panelist, the head of product at Comet, Jacques Verre. Jacques, thank you so much for taking time out of your schedule to be here.
Thanks for inviting me. I've been following the sessions and I'm glad I was able to make the last one.
I'm super excited to have you here as well, because like a lot of the concepts we talk about during these sessions, that they're not discussed as widely as I think they should be. So I'm excited to pick each one of you guys' brains and experience to get some answers to some what I think are interesting questions. And for those of you watching on LinkedIn or on YouTube or that are here in the room with us, if you have questions about anything that we're discussing as it pertains to model monitoring, model serving, please do let us know right there in the chat or the comment section. We will be monitoring them, so get all your questions in. So I'll go in order for getting answers and feedback for questions. We'll go Jacques, Doug, Dhruv, and Michael. And again, these questions are mostly here just as a guideline. Definitely want the conversation to be as organic as possible, but I did have a few questions prepared. I think the first one, a good starting point or entry point into this discussion is just talking about what makes deployment of traditional software systems so different from deployment of machine learning systems. So let's go to Jacques on this.
I think that's a very interesting question, and is in a way why so many teams do struggle with deploying models to production. I think maybe the first thing to note is It is very different, but it also comes from the same place. To deploy your models to production, you need a software engineering team. Like you need an engineering team to be able to successfully deploy your models, especially when you start having some of these really tough requirements around latency, how quickly your models can make predictions, or scalability. You will need an engineering team. However, that engineering team will need to be specialized or specialize themselves over time as they get more experience, but they will need to specialize in deploying ML models because there's a number of requirements and differences with traditional software. And when I was thinking about it, I think two came to mind. And the first one was really around the requirements. So machine learning models by design are very data heavy. You need to collect a lot of data. You need to pre-process or format that data in the right way to then feed it to your machine learning model that can then make a prediction. And it needs to do that very quickly in most cases. Like when we're talking about fraud detection, for example, you need to look at the past payment history of a person or a credit card, aggregate all of that data, make a prediction, and then return that prediction in 10, 20 milliseconds. And that's a really tough engineering challenge. And that requires infrastructures and tools that are very different from what you would use for traditional software, because you need to be able to query data very quickly. You need to be able to transform that data very quickly. And I think that's one of the things that makes it different from the traditional soft kind of systems in general, is those two data heavy versus low latency requirements. And then I think that the second part of it, and we'll start talking about it when we go through some of the kind of next questions, but I think the biggest challenge is that even if you successfully deploy your model, if you feed it wrong data, it will still work in a sense. It's still going to return a prediction. It's just going to return something, a completely wrong prediction. And so you just don't have as many errors or bugs as you would have in traditional software systems. If you're building a dashboard and all of a sudden a database doesn't work for some reason, you're going to get errors, you're going to get bugs, you're going to get higher latency, and you're going to see all of these things in your monitoring tools. You know something's gone wrong. For ML models, most often what will happen is all of that data will still go through the system, still make a prediction, but actually the system is in a broken state where you just don't know about it. And that brings a lot of additional challenges that make it very different from the traditional system. So requirements and error tracking, I think, are the two things that make it different from software systems in general.
Jacques, thank you so much. Appreciate your input there. So I'd love to hear from Doug. If I know Jacques covered a lot of ground there. So if you want to tweak the question, maybe think about the difference between, okay, we talked about difference between traditional software and machine learning, but how about like traditional machine learning and deep learning? Is there a difference between the deployment of those systems? What are your thoughts around that?
Yeah, that's an interesting tweak. And of course, I agree with everything that Jacques said. But to go with your variation, it's, I think, good to take a step back and see exactly what we're doing. And these little machine learning, whether it's deep learning or some other system, these are like little systems that are able to think on their own. And we have to treat them as that, because that's why we're interested in them. They do great things for us because they're able to do pretty good jobs on data they haven't seen before. This is called generalization. So they're able to give good answers for novel data. And that is amazing. And that's why we're in this field, because we can take advantage of those utilities, the functions. But exactly how you take that idea of these little bitty black boxes that are able to think on their own in a way, and combine that with software engineering, it's a real challenge. You can't, like Jacques said, you can't just take software engineering best practices and stick them on to machine learning. This is in some ways a new thing. When we talk about testing, or even the idea of what a bug is, these are like analogies. So we're rediscovering what a bug is. We're rediscovering or inventing what it means to do testing, what it means for something to go out of specs. So this is a really interesting research challenge. as we move forward. And it's only going to get more interesting. We're really just getting started with this idea of combining machine learning with software engineering and turning these into part of the production pipeline.
Doug, thank you so much for that feedback. Jacques, I'd like to pick your brain another riffing off the question here. So there might be data scientists who are maybe the first data scientists in an organization, or maybe they're one of the first hires of a cohort of people that are going to become a data team. And let's say these folks are maybe they get embedded inside an organization that has more of a traditional software engineering type of culture. What are some things that these practitioners can do to help change the mindset around development of machine learning systems for these software folks? I'm not sure if that question makes exact sense. Hopefully, yeah.
So I think there's quite a few things, and I've been there before. I joined a team of 4 data scientists in a company that had 10,000 employees or 20,000 employees. So it's always a little bit of a challenge when you're the first team in even a small company or a big company, and you have to bring some of this change. I think there's a couple of things. So I think the first one is to recognize that in the engineering team, they are very responsive to the challenges that we have. And so it's more about providing guidance, and then usually they're really keen to help you along with that journey. All of the engineering teams I've worked with are always super excited to work on machine learning problems. So you usually have quite a lot of enthusiasm from the engineering team that you can build off. And a couple of things that I always recommend is to always link it back to the impact that the model will have. So we've talked about monitoring, we've talked about deployment. If you keep thinking in terms of the business impact of your model, what it is that you're trying to achieve, that business impact will nearly always be monitored. It will be tracked. People are going to have quite a high vested interest in that business impact. If we talk about fraud, there are going to be whole teams that are responsible for keeping fraud low, and they're going to be tracking this. They're going to be monitoring it. They're going to have existing systems in that area. And so if you stay close to the business impact that your model will have, you're also going to be able to bring in a lot of other teams that already exist in the company that might be using more traditional, maybe statistical approaches, not deep learning ones, but you can work with them, have their expertise on the monitoring, on the deployment, on the data side of things, and working with them to then build out your solution. And in a way, you're going to very quickly have internal advocates that are on your side to push the change forward. So I think really staying close to the business impact is something that becomes really powerful in driving change.
Jacques, thank you so much. I want to get some input here from Michael, and then Dhruv, I'll go to you first for the next question. Michael, so based on your experience, because you got some interesting uses of machine learning throughout your career, I'm wondering, how you see this difference between, traditional software system deployment and machine learning system deployment.
There's 2 things I want to touch on. One of them is on some challenges that come with machine learning, and I think one of them is on challenges that shouldn't have to come with machine learning and that have to do with learning from other people. The first is that because trained model assets, right? These are usable working programs that live as artifacts that are the result of some training process. And so as a result, what I'm trying to say here is that it's much harder to have, transparency in software systems that rely on machine learning models. And especially if we're talking deep learning or something like that, we aren't really able to have code as infrastructure in machine learning the way that we can with sort of be did by plain readable text that can be stored, can be reproduced, can be diffed, all that kind of good stuff. And so this means that it is much more difficult either to have a bird's eye view of a system or to get into the weeds with it. And that's why there's this sort of emerging field of additional tooling for exploring and auditing around models as we're training and deploying them. And I think that challenges that come with integrating ML or data science work with other engineers or developers or with collaborators who are low code or no code kind of roles, it becomes really difficult to actually share all of that relevant kind of, bird's eye view information with them. Because for instance, not everyone that you work with has everything installed off the bat to, let's say, open, I don't know, a Jupyter notebook or something like that. And even if they can, to really feel at home in it. And so I think one of the big challenges there, again, comes with tooling and comes with access and transparency. And the other thing, touching on what Jacques was getting into about like the fraud detection example, and about how people in data science or ML engineers or whomever it may be are working on problems. If they are high impact, there are probably problems that other people have worked on before in other ways, and definitely that other people care about, or else what are we doing here? And so learning to sit back and listen, to incorporate domain knowledge and incorporate heuristic techniques that have been honed by experts for a long time in various, fields or problem settings is really big. And if you don't do that, and you go in with a naive approach to let's throw gigantic, uninformed, like non-domain specific or domain aware model at every single problem we see, it's like when all you have is a hammer and everything looks like a nail. And so I think it is imperative for data scientists or ML engineers or researcher scientists or whatever it is to really embed themselves in the problem setting, to try classical approaches, to learn about classical approaches, and to have a foundation of that before they just kind of throw everything through like a giant transformer or something.
Michael, thank you so much. Appreciate that. Dhruv, let's go to you for this first answer on this next question. So I'm wondering what happens when we deploy these models? What are some of the things that can go wrong? Or maybe if you wanted to tweak that, what are some of the most common things that you see go wrong?
Yeah, thanks for the question, Harp. Yeah, I can take a stab. And there's many things that can go wrong. And I think Jacques already touched on one of them, is that with ML systems, they tend to fail silently. You could have a perfectly well-functioning model and you just start feeding it in, like the input data starts becoming garbage in production, like a bunch of inputs turn into nans, or like they have outliers in them. And the model could still output a reasonable prediction, right? Because at the end of the day, it's like a bunch of numbers going in, like maybe a single number coming out. So you may never catch what might be happening with the model until someone who owns the business function realizes predictions are wrong, or you get pinged at 5 a.m. saying the model is sending shipments to Australia when it's supposed to go to somewhere else. So these are like big failures, but I guess like the core idea is like ML models can fail silently. And they can fail for like multiple reasons. This could be that your input data starts to drift. So this is when, let's say, you've trained for a particular distribution of events or features, and then in the real world, this distribution isn't really met. And so because of that, your model, the expected predictions don't really match what you had in your training set. The other thing that could happen is your target could drift. So let's say like you trained your data, your model on data that came from like pre-COVID times, right? So like sales for a particular product, let's say toilet paper, had an expected volume. And then you're predicting post-COVID time, where COVID happened, people start stocking up on toilet paper, and you cannot like keep up with the supply because there's this huge spike in your target volume. So that's how a target can shift. And I think there's another case, Jacques, correct me, I'm having trouble recalling it, like both things can shift, like your input, like your whole input domain and your target can shift. But I forget what the formal term for that.
I think it might be the covariate shift, but I'm not entirely sure either. But it's when the relationship between your input and your output changes. So while the overall distribution of both might be similar, they actually end up being related in a different way.
Yeah.
I think bouncing on what Dhruv mentioned in terms of a lot of the failure modes, I think there's a lot of discussions about data drift and concept drift in general. And those are a lot of the examples that Dhruv have mentioned. But when you think about how those happen, they tend to be long-term failure modes. It's over a period. And of course, you have events that are going to create shifts in the distribution very quick, but often there are things that are going to happen over days, weeks, or months. And there are things that you can also estimate on your training data. You can do out-of-time validation, where you train your data on data from 2 years ago and then evaluate it on data from a year ago. And then you can see, okay, how quickly over time does my model performance start to drop? And so that is out-of-time validation, which is different from the cross-validation, where you're going to be randomly sampling events. But so you can do that validation, and it can give you an indication of how quickly data drift has happened historically. Still important to track it in production, but So those are what I tend to call the kind of long-term data issue, like performance issues that you're going to see. But very often the reason why you're going to be woken up at 3 a.m. or that you're going to have to quickly shift from one project to another is for more kind of abrupt changes in model performance. And those actually end up being often tied to the system itself. So one of the examples that I've seen in the past is for your machine learning model, you ingest a lot of data. And one of the tables that we were ingesting were foreign exchange rates. So how much is a pound versus a dollar? So we could do some currency conversion. And that table stopped being updated. The database and the other team that was responsible for that table decided that it was no longer required. And therefore, they stopped updating it. The model still works. We can still do all of the currency conversion, but the data starts being out of whack. And so that will result in very quick, abrupt changes in data. And you'll also have databases that are dropped by mistake or kind of upstream data collection processes that stop working. And then you're going to have system failures. So you might actually have environments that no longer work, Python dependencies that result in breaking changes when you do an upgrade. And so I think it's really important when you're thinking about your monitoring system to think about the long term. Okay, how am I going to track the degradation in performance over a month, like a week, a month, a year? But then also, how quickly do I need to know when something goes catastrophically wrong? And those are really the two things that you'll end up having to balance.
Jacques, another kind of follow-up question from you. I know you touched on it a little bit here, but I think something implicit in what you're describing there is some feedback loops that we should be taking into consideration once the model has been deployed to production. For some of us out there, maybe we are just okay looking at things manual, ad hoc basis. Maybe our systems aren't that complex. And for some of us, we might need something more complex and some tooling out there. So I'm curious what your thoughts are. Let's say somebody is just naively trying to set up production monitoring. What are some vocab terms they could look into for monitoring? And if they're going to do it ad hoc, and then if they wanted to take it more sophisticated and just something more heavy duty, what are some options for tooling out there?
I don't know if I'm the best person to answer that question about tooling and words to Google to explore, but I guess I'd like to talk a little bit and build on what Dhruv and Jacques said about what to do when things go wrong. I think there's a category of exploration that one needs to do when things go. There's the idea of explainability and just the ethics of AI, the ethics of having a machine learning model that's making decisions that could affect people's lives. And so to talk about the feedback loop, there's some due diligence, I think, that needs to be done by practitioners, that you shouldn't naively just put something into production and start monitoring it to see if it goes out of spec. There's more responsibility than that. One really needs to know why these systems are working, and that gives you insight on when they fail, what's wrong. You wouldn't necessarily be aware of bias and other aspects of the model unless you take a more broad look at what happens after the machine learning system makes a decision. What happens then? How does that impact people? And then ground truth is great for the cases that we know about, but for cases that we don't know about, what does it mean? What is ground truth? If you're making a decision on someone getting a loan or not, does that turn out to be the right answer? For the no's, it's hard to say because you just didn't give them a loan. But for yes, you can do additional data. But you might also want to inject more humane ways of exploring the system. So every once in a while, maybe you do want to make a decision. In developmental robotics, we call this exploration. We actually give a bit of autonomy to the system. We call it intrinsic motivation. So the system could actually collect different data and maybe explore different ways. So we're not there yet, of course, but the idea that we're just putting data in and we're getting an answer out is a simple way of using machine learning. And I think since we're just on the cusp of really integrating these types of systems into production, this could get a lot more interesting and consequential as we go forward.
What you mentioned, Doug, is really important about the feedback loops is As soon as you deploy a model to production, you are introducing a feedback loop. And the example that you gave around loans is like a really good one. If your first model that you're building has a bias one direction or another, or even has a relatively high rate of people it's not going to give a loan to, then for those users or for those people, they're people at the end of the day, then you're not going to have a ground truth to be able to build your second version of the model. And so what you'll end up doing is you'll end up, for every iteration of the model, you're going to be increasing the bias. And so it's always really important when you're kind of training the second version of your model to really think about what ground truth labels do I have available? And could they be biased in a way? Are there things that I need to build into my deployment system to avoid this? So one of the strategies that is used quite often is you just take 5% of your traffic and you just don't make a prediction. You just assume everything's right so that you can have your ground truth. And that's often one of the things that's hardest to explain to people that are not building machine learning models, because they're going to be saying, why am I going to give 5% of people their loan, even though the machine learning model is telling me that I shouldn't? Like, it's going to have a business impact. But without it, you won't be able to build a second version, or you won't be able to monitor the model either. So it's really important to take that feedback loop into consideration, not just when you're building the first version, but every subsequent version is going to be dependent on the previous one.
If I could just come back with that, I agree absolutely. And in developmental robotics, we have the idea of curiosity. So it's not just 5% that you just randomly pick, but the system could actually help you. We've never given this type of data the option. We've never allowed them to get a loan. What would happen if we did? So adding the idea of curiosity to the system so it could help explore the edges of these decisions would be really provocative.
Very insightful. Thank you so much, Jacques and Doug. And Jacques is setting you up here for a plug for MPM when we talk about tooling. Talk to us about how the tool that we've built at Comet, Model Production Monitoring, MPM, helps with these types of issues.
Of course. So we've talked. I've talked a little bit about the different failure modes around abrupt versus gradual over time. And so Model Production Monitoring that we've built takes this at its core. And one of the big decisions that we've made for that is that when you're looking at trying to detect a failure within, let's say, a minute of it happening, and if you're in a really high impact, you're building a high impact model, that could already be a little bit too long. But let's say we have this one, you want to detect failures within 1 minute. In nearly all cases, you won't have access to ground truth labels. And just because they haven't been generated fast enough. So when you think about the model we were just talking about on giving people loans, you will only know a year later, 2 years later, whether or not people have paid back the loan. So your ground truth labels are very much delayed. And even if they come through quite quickly, they very rarely come within a minute or 5 or 15 or an hour of the prediction being made. And so that's why when we've built MPM, we've taken that into consideration. And every model, we end up tracking 2 metrics. We end up tracking accuracy related metrics. So accuracy, precision, recall, root mean squared error for regression models. All of these metrics are tracked, but that's really about tracking long-term performance of your model. Is my model performing today as well as it did a month ago or a year ago? And then you can start catching some of the maybe changes in behavior that your users have exhibited over that period of time. But when you're looking at those abrupt changes, we track data drift and concept drift. And the reason why we track that is because it's interesting to look at data drift over a long period of time, but over a short period of time, it also allows you to say, is the data I'm giving my model similar to the data that my model saw a day ago or a week ago or during training? If the data is roughly similar, I'm going to be relatively confident that my model is behaving as expected. I'm not going to be 100% sure, but I'm pretty sure it's what I expected. If the data starts being very different, then I can be like, I don't know if my model is broken because perhaps it can cope. And that's what Doug was saying at the beginning of the session. Maybe it can cope and generalize to this new data that it's seeing that it hasn't seen before. but I'm not entirely sure. I should probably take a closer look. Let me just double check and let me see what's happening. And so that's where we find data drift metrics to be really powerful, is around these short-term performance degradation detection. That was a little bit long-winded, because there you can compare that very efficiently. And really, you can collect a few data points, compare them to training. You can collect hourly data, compare it to your training data. You can even compare it to different periods. So that's some of the things that we've built into NPM to tackle some of the challenges we've already mentioned.
Jacques, thank you so much. And love to hear from maybe Michael and Dhruv on this. You know, as someone who's been heavy into traditional machine learning methodology throughout my career, it's very easy for me to understand the concept drift when it comes to statistical distributions of, let's say, a feature, like a column, something like that. But when it comes to like drift with unstructured data like text or images or audio files, is it the same thing that we're looking at, or are we looking at something different? Like I'll open it up to Michael or Dhruv, but if Doug and Jacques want to jump in.
That's a really good question. And actually, like, I've seen that question arising just in, I don't know, I suppose like Twitter discourse and ML circles recently, not to be like misleading, but like a little bit opaque with regards to, like unstructured, high dimensional, like implicitly high dimensional data, especially like text. For instance, if we think about what a mismatch of distribution across like two text corpora, like two like bodies of text, like data sets or contexts, we can't think of it as like this versus this, because the differences that shape the content of two different bodies of text are sometimes very explicit, like this one's in, I don't know, Spanish and this one's in French. Sometimes they're very implicit. This one is centered around a particular domain and this one isn't. One really interesting aspect of distributional shifts in, I guess, like a multimodal setting, which is to say images and text. If you think about like big multimodal models these days, like things that combine computer vision with large language models. So stuff like CLIP, right? Contrastive language and image pre-training, where you have these massive internet scraped data sets and you are comparing images to their alt text or captions or other like nearby text. And people use these for a lot of different things. And even in the field of large language models, like one of the distributional shifts that we're going to be facing in the next, we're already facing it now, is that these models are going to be aware of themselves, because images produced by these models or text produced by these models and text models, and that's about text about these models, is going to start showing up in training data. And that's a distributional shift, and it's very implicit, right? Like these are ideas that are represented. It's hard to talk about a mean or variance or some like moment of a distribution shifting, but there are these abstractions that are like emerging in the data that are causing behavior to change. And soon, if you are working with CLIP plus some sort of like image visual transformers, make generative art or something, and you want to put in a prompt and you say generative art or like CLIP-based generative art, you might be using a language model that has seen pictures made of that. And so you have another sort of reflexive situation where a model is informing itself, and that's causing a distributional shift. And that's really hard to measure, because it's I think the best we can say is that it's high dimensional, but that doesn't really capture the sort of like concepts changing. That's something that I like to point to when I think about like distributional shift in deep learning and in like multimodal data.
I think there's just putting a few pointers in terms of how could you monitor image or text models. Like it's very hard to do, and I don't think anyone has converged on the best solution, but there are a few things that you can do. So maybe the wackiest idea in a way that I have seen in terms of monitoring these models is actually to use machine learning to track your machine learning models. And so the way it works is you take your training data, and so that can be images or text. You take your production data, your serving data, and then you associate the label, which is whether or not it's training data. So it becomes a binary classification problem. You have some text or some images that are training data and are 0 or are 1, and then your serving data is 0. And then you try and train a machine learning model to identify which images come from your training data set and which ones come from your serving data set. If you can build a model that does that, then they are fundamentally different. They come from different distributions, and there is a mathematical way of separating your training data from your serving data. If you can't, and you always have an accuracy that hovers above 50%, then it means that fundamentally those two things are the same, and that there is no significant differences between the two. And what's really powerful about this approach is that if you can build a model that separates between the images, you can start looking at the images that it identified as different. And then you can be like, oh, okay, I didn't realize I had 5% of blank images in my serving data that I didn't have in my training data. And you can find those because the model has said that they were different. The problem with that approach, of course, maybe the reason why you can't separate between the training and the serving data is because your model is not powerful enough. Maybe it's not big enough. Maybe it doesn't have the right architecture. And then since you're monitoring a model using another model, then how do you monitor the model that you've used to separate the images? So you get into this infinite loop, but it can be powerful in identifying outliers. That's the most complex solution. I think one of the things that I always recommend in these cases is go back to your business understanding. Do you know what your data should look like? If you're working on text, do you know whether or not your text should never be shorter than a certain number of words or characters, or never longer than a certain number of characters? Are you able to simply find a proxy metric so you can look at the number of words of like nouns, for example, and then you can track that over time and see if that changes? Or you can look at where the data is coming from. You might be looking at customers, or you might be looking at some of these proxy metrics. So go back to your business understanding of your problem when you're working on text and images, and see if you can come up with summary statistics. Like another good one for images is like, look at the average sharpness of the image and track that over time. That becomes super simple. It's a single number. You can look at the distribution of the image sharpness over your training data set, over your serving data set, and track that over time and monitor that. So go back to business understanding and then look for proxy metrics. Is usually the easiest way to get started, at least. And that will give you some confidence that your model is behaving as you expect.
Yeah, big +1 on that, like really like practical approaches there. And definitely in fields like computer vision, like being able to rely on like more classical image metrics, like you mentioned sharpness, Jacques, is like a super good one. That sort of thing can be really helpful too, because you might discover another type of distributional shift, and one that could happen really rapidly is, let's say, if your training data and your production data maybe consists of like images taken by users, consumers, customers, etc., on like mobile devices, cameras change sometimes really radically. So if all of a sudden everybody has a 1 billion megapixel, camera in their phone, and you're downsampling that to put into some like deep CV model, that's going to have like really like weird artifacts and those things like might be more transparent to like classical computer vision metrics. And yeah, like relying on those is really huge. And it also takes us back to collaborating with like classical domain experts and stuff like that.
Doug or Dhruv, anything to add here? Dhruv, let's go to you first.
Yeah, I was also going to talk about using another model to monitor your existing model, and like the whole loop that you fall into. It's a trap, but it is a very interesting approach. Yeah, I think with like deep learning models and like unstructured data, if you are trying to model like the features of a deep learning model, let's say convolution net, the issue here is like the feature is like this high dimensional vector. It's very difficult to get like a distance metric for this. It's like cosine similarity, mean square error, but it's not 100% guaranteed to work. But like an interesting thing, like using these proxy metrics is actually like probably a very good way to get started. So +1 for me on that also. Let's say you do want to monitor images coming in. What if instead you monitor just like the camera version, like you logged the camera version and all like the settings of the camera. So then you just track like real information. So version number changes, chip architecture, something changes. So instead of tracking some super high dimensional vector, you can rely on like the more traditional ML statistical monitoring techniques to detect through proxy metrics. It's a good way to get started. And then as I guess research and development sort of improve, we might get better ways of monitoring like just like images for image content itself, or text for text content. Yeah.
Dhruv, thank you so much. Doug, any inputs here?
I just say that I'm a big fan of pitting two machine learning systems against each other. That was always the suspicion of that's how we're going to get the next level of intelligent systems throughout history. And it's turned out to be a really powerful way of creating models. And to go back to something that Michael said about just, we're not looking at the data per se, we really are interested in the concepts and the representations of what these systems believe. And in the history of neural networks, we thought that was going to be the problem. That's what we had to solve. We had to come up with the systems that created the right concepts and ideas inside the hidden layers of a neural network, for example. But it turns out that we largely didn't do that. We now have these systems where we don't pay too much attention about what's going on inside. But I think as we move forward, we'll have to, especially when it comes back to the ideas of explainability and transparency and understanding what the model is doing itself, we'll have to have get better insights into the concepts and ideas inside these black boxes.
Hope everybody was taking notes there, or at least we'll run back and listen to all that stuff. Some great insights there. Thank you guys so much. So I guess if we've got a few minutes left and I got a few questions, I've decided which one I want to take it, which direction I want to take it here. I guess we can talk about continuous experimentation. I know that's something that we like to talk about a lot at Comet. Jacques, talk to us about this concept of continuous experimentation. How can we, close the gap between production and the development process?
I think it's one of the reasons why you have monitoring in the first place, right? It's like monitoring is important so you can know if your model is performing as expected, but it's also a really important input to know how to improve your model. If you have the right monitoring system in place, you will know where your model performs well and continues to perform well, and where your model doesn't perform well. So one of the things we have in NPM, in model production monitoring, the Comet monitoring solution, is segmentation. So you're not just looking at the model performance overall, you can also break it down by country, for example, or any other dimension that's important to the problem. And through that, what you'll then be able to do is, over time, you can see, oh, my model performance overall is pretty stable, but performance is degrading in France, for example, or from data that comes from that country. And so that can then inform the next version of the model that you build. And so armed with that information, you can go back to training. So first of all, your monitoring will tell you when you need to retrain your model, but also where to focus your efforts. And then you can go back to the training loop and kind of iteration cycle. You can keep iterating on your model until you've either fixed or improved your model in a certain area, and then you'll be able to deploy it. And then that becomes that continuous loop of, I deploy my model, I see how it performs. If I find an area that can be improved in the model performance, I can go back to the training. And what's really important there as well is to keep all of that linked. When you're retraining a model, it's really important to then be able to compare, when you're in production, to compare the performance of your new model versus the previous version. And so that's some of the things that by having a really strong monitoring tool in place, you'll also end up having a much more informed training pipeline because you'll have all of that information available.
Doug, thank you so much. Doug, anything to add there to this notion of continuous experimentation?
No, just to say, yeah, I agree with Jacques' point, but it's also an open research question. As we go forward, there'll be new ideas to explore better ways of measuring. So yeah, it's an exciting time to be in data science and machine learning. There are just so many possibilities for not just deploying models, but moving forward into unexplored areas.
Doug, thank you. Let's go to Dhruv and Michael on this. Talk to us about your thoughts around continuous experimentation and how we can bridge that gap between the model development process and the deployment monitoring.
I would say jumping off of Jacques' idea of something like segmented production, like metric monitoring. Ultimately, I think what we're describing is something where continuous experimentation is fundamentally a very human in the loop process. This is an augmentation process. We're augmenting what people can do with machine learning and vice versa. And I think that's what needs to be kept front and center. Is there are some things where, human kind of like intuitive analytical reasoning or abstraction is like really able to dig in quickly if we, navigable tools to identify those kinds of things. So I think this is basically all about the ways that people and ML software can augment each other.
Yeah, let me take a stab at this. So I think it was Andrej Karpathy or maybe David Ha like recently tweeted about this. It's like production is the test set. So like personally, I just get very frustrated with the concept of a test set. Like I just don't think it really provides a lot of information, because after, let's say I've created my model and I train on I evaluated on my test set that I have not looked at, and the performance is bad. What do I do now? Do I just throw the whole thing away? So I'm a very strong believer in try to get to production with whatever you can as quickly as possible and monitor your intended use case. So what are you trying to predict? How is that data changing? And if you were to have like an Oracle model where you can manually label like some set of data with the expected prediction, does it impact your business metric? Can you correlate the two or draw some sort of connection between the two? So I think, with continuous continual learning, your experimentation should start, or at least get to production as quickly as possible, and then based on the real world data and how that's changing, inform the more advanced development of your model, if that makes sense. So put your baseline heuristic, whatever it is, simple rule, into production as quickly as possible, monitor the data and how it affects the business use, and then start iterating from there. So that's my definition of continual learning.
Thank you so much. Doug, Michael, Jacques, Dhruv, thank you all so much for joining us today. A lot of great insight here, a lot of great learnings from all of your collective experience. So I hope you guys do get an opportunity to go back and listen to this if you're catching the tail end of it. And you can also go back and listen to the last 7 weeks of Office Hours, where we had many more sessions just like this, jam-packed with a lot of interesting, insightful content that I don't think gets discussed as much as it should, and some of the most important parts of machine learning. My friends, thank you so much for joining us, and all of you watching, thank you for joining us as well. Remember, you've got one life on this planet. Why not try to do some big? Cheers, everyone.